And the second theorem gives us the pointwise So I thought rather than just say the theorems hold, I'd give you some details, but it's quite technical, but a lot of stuff about maximal functions on Lie groups, Harish-Chandra's theory go into a proof. And if you know all that stuff and you know the proofs I gave at the beginning, then you can put it together and get these two things. Hmm? G is acting on X. So, yeah, X, B, mu is a measure space, and then you have an action of the semi-simple group on the measure space. So I'm not going to mention anything about analogues of von Neumann's and the other ergodic theorems anymore. I'm going to now talk about invariants, which allow us to distinguish between various actions, because there have been some quite interesting invariants that have come out in both the areas of discrete free groups and in the area of semi-simple groups recently, and in fact, as a kind of analog of is the shift on 2 generators, can that be isomorphic to the shift on 3 generators? There was a problem hanging around until 2000 of can an action of the free group on 2 generators be equivalent, isomorphic to an action of the free group on 3 generators, and nobody knew how to distinguish between actions of those groups. And I guess, so this is a question I should have looked up the date, I haven't. And fortunately for suffering humanity, the answer is no. And this was proved by Damien Gaboriau in about 2003, who's from Lyon. So I thought I might spend a bit of time telling you how the theory of costs works and why that distinguishes between the actions. There's been a great deal of interest in the theory of costs. It's mostly been used in the case of, I suppose, countable or discrete groups like FD, but I don't know, we need a sort of semi-simple version of costs, I think. So here's the theory of costs. in a bite-sized package coming to you today. So at the moment I'm not even going to give x a measure. We want to think about some of this stuff was worked out by, well, it was worked out by Leavitt and people like that who are not harmonic analysts, but Gaboriau managed to apply it to harmonic analysis. It's kind of graph theory, it's the theory of equivalence relations. So let's say x relates to y if there exists a g in G with gx equal to y. So we're thinking of x, and these are orbits really. There's x, there's gx, there's g squared, or g1, g2x, etc. So all the points on a group orbit are put into the same equivalence relation. So a graph So the question we want to answer is, how big are these orbits? And in fact, what might happen is that I can get from this point of the equivalence relationship to that part of the equivalence relation in several ways, using several different group elements. What we want to do is strip away these several different ways and work out how the minimal way that you can get, and that gives you an idea of the size of the orbits. So we don't want orbits with loops in them. Orbits with loops in them are bad because there's redundancy there. We're trying to work out the size in some sort of Borel measurable sense, what the minimum size of an orbit is. So a graph and some equivalence relation which is not reflexive, that means x is not in R, and for any x, and symmetric. R minus 1 is it? Well, maybe I'll call it G, curly G, that might be a good. G minus 1, of course, is if you take x, y, y, x. A cycle sorry? A graph is not an equivalence relation, I'm terribly sorry. A relation. Which satisfies these two things. It can't be an equivalence relation and a graph, unless it's empty or something. So we want to work out what the Borel equivalence relations are, and we want to talk about graphings of equivalence relations. now I'm talking about equivalence relations. I'll call it curly E maybe, is a Borel equivalence relation if E contained in X cross X is a Borel set. That will happen for one of these these G action things, of course, if we've got some sort of Borel action of G. And E is countable and that happens, of course, if the group G is countable. So the example is gamma is a countable group and gamma X goes to gamma X is a Borel action. And there's a theorem, 1977, Feldman and Moore. Every countable equivalence relation So it appeared that we'd got a long way from groups, but in fact we're still within groups. A Borel section means if it meets each equivalence class once, I'm going to use some notation so E is the set of Borel isomorphisms with f of x, E, x. So, for example, multiplying by a group element keeps you in the same equivalence class, but there might be other Borel isomorphisms which do the same for us. And E is a set of local Borel isomorphisms, F from A onto B, So let's suppose now a countable group could be one of these amenable groups, could be the free group. preserving the measure mu. A graphing of the equivalence relation I waffled vaguely about somehow finding the smallest size of an orbit. This is what I'm attempting to do by what I'm about to do. L stands for Leavitt. Everything's a Borel function here. And these have to be some of these local Borel isomorphisms. So let's supposing that phi I maps AI onto BI, which generates E. That means X relates to Y if and only if there exists a sequence a finite sequence, in fact, I1 up to Ik, of elements of this index set of the functions I, so a finite number of functions, and epsilon I in plus or minus 1. So that, just like the free group action in some ways, X is equal to phi I1 epsilon 1 phi I2 epsilon 2 phi Ik epsilon k. So the question is, I've got this equivalence relation which might be generated by a group or something, and I want to find a graphing, so that's a minimal set of group elements, if you like, that get me from A to B inside the equivalence relation. So that's a boring graphing is the set of all elements of the group, which will do this for me, but there could be more interesting graphings, and we can define what a small graphing is. So let's add up the domains, the measures of the domains AI of these functions. And that's called the cost of the graphing. So I want to kind of make the domains of the functions small so that it's kind of making a little tube around my orbit. How small can I make that tube? That, of course, is the same as measure preserving. And the cost of E, so E is some equivalence relation. What do I mean by the cost of that? I mean the inf O over the costs of all possible graphings. And I need to put the word almost everywhere in there to make it sense. So what I now want to do is say the cost of the equivalence relation, which might be that generated by a group, but this holds more generally, is the smallest cost of any graphing of the equivalence relations. So this notion was introduced by Levitt in 1995. And of course, it's some number between 0 and could be equal to infinity. So what I'm going to tell you is that the cost of a group's action is an invariant for the equivalence class of the measure, and it's one that actually enables us to distinguish between groups on D generators and E generators. Now, you can even get better something to So the best sort of a graphing is a treeing, and that says you take any word like this, phi I1 to the epsilon 1 up to phi In to the epsilon n, then the set of all x in the domain of the word such that Wx equals x is empty. So that's the most economical kind of graphing that you could get. It's a tree that says there are no loops. If you had Wx equals x, there would be two different ways of getting that way. So we don't want to be able to go around a closed loop inside the thing. So now I'm going to tell you about Gaborio's results. There's 2,000 he proved them. So let E be a countable equivalence relation. Mu on E an invariant measure. With the cost of E being less than infinity. So let's suppose that phi is an L graphing of E which attains the cost. That means that the cost of E, which is that inf thing, is the cost of phi. Then phi is an L tree. Of E almost everywhere, and we call such a thing such a relation treeable. I never tried to read it in French. I wonder if that's arbrable. It's quite hard to say in French, isn't it? Treeable. Anyway. So here are some of the results of Gaboriau, which on the costs of groups. So if F's a countable Borel equivalence relation, S a complete section, then the cost of E is equal to the cost of mu restricted to S, E restricted to S plus the measure of X take away S. So it defines the cost of a countable group gamma, C of gamma, to be the inf of the costs of all E such that E is induced by a free action. So take the smallest equivalence relation, the cost of the smallest cost of an equivalence relation induced by a free action of gamma in that sense that I first said. So the question is, what are the costs of various groups? So I'll write down some costs for you now. I gave a talk on this at the University of New South Wales, and people came from the economics department to listen to me because I was talking about costs. But they went away quite quickly after the first 5 minutes of the lecture. If I have a finite group, the cost of gamma is 1 minus 1 over gamma, the number of elements of gamma. If gamma is infinite, cost of gamma is greater than or equal to 1. What about amenable groups? The following are equivalent.